Welcome everyone. My name is Rajesh. In this talk, we are going to discuss about our paper, Effective Parallelization of the Vehicle Routing Problem. This paper is co-authored with Somesh Singh and my advisors, Professor Rupesh Nasre and Professor Narayanaswamy. Let's get started. So the capacitated vehicle routing problem, or shortly called as CVRP for rest of the talk, is as follows. So what is the input? Input contains n nodes, which includes the depot and the set of customers scattered on a two-dimensional plane along with their xy coordinates. Each customer has a non-zero demand. The vehicle has a maximum capacity limit for each trip. Node 0 is called as a depot, and note that it has zero demand. What is the output? Output is a set of routes serving all the customer demands respecting the vehicle capacity. It is important to note that each route must start and end in the depot. Right. So the goal of CVRP is to minimize the total distance traveled by the vehicle. Right. So let's understand through a small example. So notice that node 0 is a depot and customers are numbered from 1 to 4 in blue. Right. The demands are mentioned just below the nodes. And the vehicle has a capacity of 3 units, which means it cannot carry more than 3 units of demand per trip. Notice the demand for the depot is 0. So what is the sample solution for this example? One possible solution is the following. So the route 1, which starts at a depot, goes to customer 1, customer 2, and back to depot. Similarly, a route with dashed blue line starts at the depot, goes to 3 and 4, and back to the depot. So this is one possible solution, right? Notice that we have 2 routes in this solution because of the vehicle capacity constraint. We cannot accommodate even one more customer inside a route because in each of the routes, we have already reached the maximum capacity 3. So this CVRP problem in general is NP hard, right? This problem is a generalization of traveling salesman problem. How? If the capacity of the vehicle is equal to the sum of demands of all the customers, then CVRP problem reduces to the famous TSP or the traveling salesman problem, right? Then, which basically means that we will have only one route in the output, which is to minimize the total distance traveled across all the customers. That's the statement of traveling salesman problem. The motivation for our work is the following. The current state-of-the-art GPU implementation works only on smaller instances. It has a large solution gap. What do we mean by gap? Gap is nothing but the percentage of deviation from the actual solution that we output to the optimum solution or the best known solution. So it takes a lot of time on larger instance. For example, to give you a glimpse, these are the largest few instances in the CVRP literature. Even the fastest base case or the GPU implementation takes more than 140 minutes to compute the solution for largest instance called Flanders 2. So one natural question is, can we reduce the running time? Yes. In addition to it, we ask few more research questions. Can we invent a simpler algorithm? Can we reduce the gap on larger instances? Can we design parallelization-friendly algorithms? We answer with PAR-MDS all these questions positively. We have come up with a serial and parallel implementation of PAR-MDS algorithm, combining simpler algorithms such as minimum spanning tree and DFS inside it. We crucially use local search approach and randomization approach to our benefit to output a solution. Let's understand how PAR-MDS works. Okay, this is an overview of PAR-MDS. The input for the CVRP problem, we convert it into a graph. Basically, we convert the CVRP instance into a complete graph, edge-weighted complete graph. We run MST on it. We use Prim's MST algorithm to compute minimum spanning tree on it. On the MST tree, we randomize the order of neighbors in the MST tree. We then do a DFS traversal from the depot. We convert the ordering that we got from the DFS traversal into a set of routes. We then refine the route to see if we can possibly improve the route that we have got, and finally output the solution from the refinement step. So the crucial step in PAR-MDS is this randomization and the DFS thing. So the randomization actually maneuvers the nearby solution by iteratively local search on the neighborhood solution that are available for the CVRP problem, right? So we run these 3 steps in loop for a fixed number of times, which we call it as super loop. We also take benefit from the parallelization thing, and we make the PAR-MDS run faster using the parallelization. Let's understand our algorithm by running it on an example. Notice that the example is little more involved so that we understand the intricacies and the techniques involved in the algorithm. So again, this has node 0, which are in green, and 6 other vertices, making it the total to 7 nodes. Vehicle has a capacity of 5. So this would be the complete graph for this CVRP instances. Notice that the demand is mentioned just below, beside the node. Also notice that in the figure, some edges are marked in thick edges. So these are nothing but the MST edges on this complete graph. So as I mentioned that this is an edge-weighted complete graph. So how does the weight get calculated? Weight gets calculated by the Euclidean distance between the 2 nodes, any 2 nodes, right? So this will be the output solution of the PAR-MDS, which has 2 routes, one with orange thick edges and one with dashed blue edges. So which basically the cost of this route is 66 point something, whereas the optimum is 63 point something, which is just 4% away from the optimum. Right. So how do we get to second figure to third figure? Let's zoom in to the algorithm and understand how does it happens. For the sake of easier understanding and visualization, we have rooted that algorithm in a tree-like fashion, rooted at depot to look like a tree-like fashion. Okay. So we run DFS starting at the depot to compute the ordering of the customers, so which gives us this ordering. We then split the ordering into routes. How do we split? We use the vehicle capacity as the key to split the routes. So notice that the route 1, 3, summing up to total of 3 demands, and which goes into route 1. So we cannot add 4 into route 1 because then our capacity would exceed 5, right? Which is the maximum capacity allowed per route. So similarly, route 2 will have 4 and 6, which makes the route's capacity to reach its limit. So we cannot add the next customer into route 2. So this is how we make the permutation convert it into a route. Once the routes are calculated, then it is then easier to calculate the cost of the route, which is basically the sum of distance traveled in all the routes. Right. So how does we get to a neighborhood solution? Yes, this is what I'm going to explain it next. So randomization of neighbors basically interchange the neighbors. So in this case, 3 and 4 of neighbor 1 gets interchanged to the second configuration. Similarly, the nodes of the depot, the neighbors of the depot 1 and 3 can be interchanged to give a third configuration. So similarly, nodes of 3 and 4 can be interchanged to give a fourth configuration. So this 4 configuration or some sample configuration which the randomization can lead to, and each configuration can lead to a different traversal ordering and which in turn produces a different cost. So the key takeaway here is the random step may involve different DFS ordering, thereby a different route. That's the takeaway from this slide. So the final step, what we do is intra-route optimization, which is called as 2-opt in the TSP literature. We perform 2-opt optimization for each of the route individually and also in parallel. So in this case, we see a crossover between the edges or crisscross between the edges. We basically have to use 2-opt to remove the crossover. Right? So basically, we rotate the sequence of edges that are in the crossover to eliminate this intersection. Thereby, the intersection is removed. More importantly, when the intersection gets removed, our cost gets improved as well. We show the effectiveness of PAR-MDS by running the experiments on 130 large instances. These instances are categorized into X instances, golden instances, Belgium instances, and other instances. Right? We run our algorithm on Intel Xenon CPU, which has 40 cores clocking at 2.4 GHz with a 64 GB RAM. So all the baselines, all the GPU baselines are run on NVIDIA Tesla P100 GPU, which has over 3,500 cores and 12 GB global memory using CUDA 11.5 version. So our code, our sequential MDS runs using GCC 9.1, whereas our PAR-MDS uses OpenMP parallelization, which is run on NVC++, NVIDIA HPC SDK, the latest NVIDIA HPC toolkit. We show the effectiveness of PAR-MDS comparing with other baselines, and we show the average speedup in the figure. We also show the total average among all the 130 instances. We get a speedup of around 36x to 1100x when compared to the other baselines. Notice that some of the baselines did not run on few of the instances, whereas PAR-MDS did run on all the 30 instances. So the gap at the end of each iteration, gap at the end of super loop, gap at the end of refinement step is plotted in this figure to know how much each step in the algorithm is reducing the gap to. So we understand the gap is improved at each step in the algorithm. So overall, on all the 130 instances, we get a gap of close to 11%, whereas the baselines were giving a gap percentage of 17% or even more than 17% for some instances. Right. Check out more details in the paper, and we highlight one more point. All the 130 instances completed close to 3 minutes of time, whereas even the largest Flanders was taking more than 2 hours in the fastest GPU implementation. So to summarize, GPU parallelization had limitations on larger instances. It was taking larger time and has larger solution gap, but our techniques resolved all these limitations by using a simpler algorithm or techniques such as MST and DFS, and it uses parallelization and randomization to a greater benefit to achieve this great speedup. So our code is open source and it can be found at this GitHub link. Our parallelization technique can be easily extended to other iterative local search or genetic algorithms. As a future direction, PAR-MDS can be extended to run on GPUs using OpenACC. It can be also incorporated direction of local search techniques. It can integrate intra-route optimization in the refinement step. We have addressed some of the future direction, and we can expect it to see a follow-up papers very soon. Thank you for listening. I would like to take any questions if any. By the way, I'm also looking for postdoc in parallelization. If at all anyone has any suggestion or leads, I'm happy to discuss later. Thank you. Thank you once again.